This is Project 42, exploring the feasibility of robotic teleoperation for visually impaired individuals. We're a part of the Heracleia lab at UT Arlington under the supervision of Dr. Ophelia Macedon. Assistive technologies, like telerobotics, have the potential to provide visually impaired individuals the ability to perform various tasks in industrial settings, like warehouses, where they may deal with static obstacles such as shelves and dynamic factors like moving workers and machinery. This project integrates audio and haptic feedback to facilitate remote robotic operation in warehouses. The research aims to boost accessibility in robotic systems for industry, particularly for the visually impaired. The teleoperated robot simulation environment is developed using the Unity game engine. The setting allows users to practice remote navigation and object manipulation. The robot can be controlled using a Sony DualSense controller, which provides advanced haptic and audio feedback to control spatial and environmental cues. The haptic feedback system uses adaptive resistance and vibrations to help users sense obstacles. A designated algorithm calculates the distance between the robot and the obstacles and relays adaptively changing haptic feedback alerts to the user when the robot is close to stationary or moving objects. Increasing vibration frequency indicates increasing proximity to objects. Audio feedback provides real time sonification of the environment. These cues inform users about object locations and obstacles, while voice prompts and sonar like pings guide them toward specific targets. The AI navigation tool voices the distance and angle from the robot to the destination using clock position conventions, where 12 o'clock is directly in front of the user. For those with some vision, visual augmentation includes high contrast overlays for visual elements and the navigable path. The system is tested by visually impaired users and trainers from Austin Lighthouse. Pre-test surveys evaluate familiarity with robotics and assistive technologies, while post-test surveys measure usability, cognitive load, and overall satisfaction. Performance metrics includes task completion rate, error rate, and learning curve analysis. Additionally, behavioral and psychological data will be explored in future iterations where wearable sensors are used to track stress, anxiety, and fatigue during teleoperation. The user study is divided into three distinct phases. Phase 1 is dedicated to testing participants in basic navigation using the telerobotic system. Participants undergo a structured tutorial with basic navigation, where users learn to control the robot's movements using the controller while becoming familiar with haptic and audio feedback. They then practice obstacle detection and avoidance, using vibration cues and spatial audio to understand object proximity. Finally, they engage in object interaction and manipulation. Phase 2 involves task based teleoperation to assess user performance. In the navigation challenge, users must move the robot through the simulated warehouse environment while avoiding static obstacles using the feedback tools provided. This phase assesses the user's ability to process non visual feedback effectively. Phase 3 increases the complexity by adding dynamic elements that simulate real world challenges such as moving pedestrians or machinery. This phase evaluates how well visually impaired users can handle dynamic environmental changes using multimodal guidance. The motivation behind this research project stems from the need to expand the independence and employment opportunities of visually impaired individuals. Current teleoperation frameworks are predominantly designed for sighted users who can rely on visual feedback and react accordingly, which creates a significant accessibility gap for visually impaired people. To bridge this gap, there is an essential need to explore telerobotic technologies that incorporate non visual feedback, such as haptic and auditory cues, in order for the visually impaired to navigate dynamic environments with their independence, confidence, and safety in mind. Beyond warehouses, this approach can be extended to other industrial and service domains, paving the way for more comprehensive robotic procedures. Future versions could incorporate AI driven enhancements, adaptive feedback mechanisms, and more sophisticated environmental mapping to further enhance usability.